Hello, everybody. I see we have the room filling up. I'm just getting the live stream going now, and then we will get started.
It's always reassuring to see people there. It's like,
Okay, I think we'll go ahead and get moving. So thank you guys for joining us for today's webinar. We have Tim Massey, our VR and engineering product manager here to take us through our recent accuracy project. The project, the background, the results, and then the next steps. So like the other webinars, I have the Q&A section open, so you can start submitting your questions anytime. I'll hold on to those, and then we'll do questions at the end. We have one more webinar in this series next Wednesday with Dr. Tom Shannon about the overlap of clinical research into animation. So definitely join us for that one. The registration link is on our social channels, or you can message me and I'll send it to you. Before we get started, I'm going to kick off with a couple of questions for you, just to get an idea of what the use cases are and if you have any experience with our FAQ section currently on the website. So that'll be good to check out afterward if you haven't seen it already. But those questions are up now if you'd like to submit. So we'll give those a couple minutes, but otherwise I will hand it off to Tim.
Thanks, Alicia. Hi, everyone. Thanks for joining. It's a pleasure to be here today. Hope you've had a chance to look at the other webinars we've done in this series so far. I think they've been really great. And like Alicia said, we've got a great one coming next week as well. Today, we're going to be talking about a piece of work we did at Vicon earlier this year on accuracy. So just to introduce myself quickly, my name's Tim Massey, if we haven't met before. I am the Vicon product manager for engineering and VR. So this is a piece of work I was involved in along with some of our team. Just to introduce myself briefly, before this, I worked for several years in various areas of robotics, primarily pick and place machinery, and then moved to Vicon almost 2 years ago now. So I'm a relative newbie at Vicon. We've got some really great team members here who've been here a long time. And this was something that I got my teeth into earlier this year. So hopefully you'll find this useful and interesting. And like Alicia said, we'll have a good chance for some questions at the end. So you might have been able to read about this topic already on our website. You'll find some material already on vicon.com, and we'll point you towards that at the end if you'd like to see some further reading. So for those of you that's read that on the website already, some of this might be repeated. You may well have seen some of this already. Of course, we want to make sure that everyone who's joining, who may have not had a chance to see that already, has the full picture. But yeah, so hopefully this session will not just talk about some of the results and what we actually did, but provide some context to the project and what we're trying to achieve, and how it give us a bit more time to talk about some of the nuance and details as well. So we'll try and add some context as we go. So yeah, so like I said, we'll provide why we did this project, why are we here? And that context, I think, is important as we go through. We'll talk about some of the variables involved in motion capture in general that may well be familiar to many of you, as if you had extensive use of a motion capture system before, and also some of the important terminology. We'll talk a little bit before we get into the outcome of the project about what method we were using, why we were using it, and we looked at a couple of different options. So I'll touch on the method we decided and why, and some of the pros and cons of that. Of course, we'll cover some results and some takeaways and conclusions at the end. So why are we here? And this is a question that many of you may have wondered or asked, or it's something that I've asked myself. Like I said, when I joined around about 2 years ago, it was one of the first questions I had from my past background. Well, how accurate is a Vicon system? And superficially, this is maybe quite a straightforward question, but it's actually quite detailed and there's quite a lot of nuance and complexity to this. So as we go through this, we'll try and answer this in a good way, and hopefully you'll come away from this session with a good understanding of what question we're really asking here and give an idea of what that answer might be. So like I said, we're aiming to be really in this session and in project in whole, the main aim is to be informative. We want you to feel like you understand more about the data you're getting out of the system. It is a complex topic, so we'll be looking to simplify that and cut through some of the details and make it easier to understand. What would you expect out of the system? Some of the common terminology, like I've said, and a method, a discussion about what performance you can expect, what is representative from a system, and why, and also provide some understanding of how you can get that performance, some watch outs about why you may not get that. And ultimately, us at Vicon, something that we were really keen to do is provide a benchmark for us. So what is the line in the sand? And as we move forward, it's a way to talk about developments as well. So before we get into motion capture, I thought we'd start with quite a simple example to try and explain the problem a bit more fully. So hopefully many of you on this call are familiar with this type of device or something very similar. And generally, depending on what you look up, a tape measure is considered to be accurate to plus or minus 0.01 of a millimeter, based on how good your eye is, if the markings are every 0.1 of a millimeter or so. Sorry, 0.1 of a centimeter, I should say. But this is we'll talk about, this is probably pretty much a best case scenario. And we know that because this type of thing happens. When we're taking measurements, maybe you've had an accident measuring up a new kitchen or something at home, or something similar. If it really was accurate to that level, this type of thing wouldn't happen, but it does from time to time. So even for a relatively simple piece of equipment, sometimes you don't necessarily get the result you would expect. And yeah, so going back to the tape measure, why is this? Well, there are some quite obvious variables involved. Were you tired that day? Did you read the number the correct way? Was the lighting a bit off in the room? Did you misread the number that you saw on the tape measure? Outside of that, is the tape measure in the right place and is it straight? Did you interpret the number correctly? Did you confuse maybe the material and imperial metric and imperial measurements on the tape measure? All of these are possible things that would give you a different outcome. Some are obviously more significant than others, but could contribute to quite a different result. And motion capture systems are no different from that. There is a number of different variables involved. Some you may well already be more familiar with than some others. But there's quite a diverse range of variables of all different types. Some of the more common ones that will come up is well, how many megapixels is the camera you're using? Clearly, higher pixel density on the camera provides better data into that system and will have an impact, and that's well known. How good are the algorithms that do that tracking? How good are the calibration algorithms that interpret that data? But there's also some other variables as well that are not directly related to the system. What is it that you're measuring? What properties does it have? What shape? What speed? Is it sometimes hidden from cameras by other objects or not? Both are possible. And then outside of the object, there's other variables as well, which are probably could give you different results even from test to test or run to run. Has the temperature changed in the room? Has the mounting of your cameras not been secure, and as a camera dropped? All of these are possible things. Even down to how do you discuss the results? Like, are you using the right terminology? Are you talking about exactly the same measurement, for example? And all of these contribute to overall error. And you can sort these out into categories. So I would see this as there's three broad categories, somewhat subjective, of course, but the first one is the probably most commonly discussed. What is the specification of the system? How good is the resolution of or how high is the resolution of your camera? What are the algorithms involved? Lens, focus, setup, system parameters. There's more than there are on this slide, of course. The next set is the environment. So even with the same equipment and same system, there are things you can change. So a good example of this would be the layout, for example, of where your cameras are placed. That can have an impact. Like I talked about earlier, the properties of the objects that you're measuring it will have an impact, and we'll actually talk about that a bit more as we move on through the presentation. Another important factor or set of factors is simply or largely due to your method. What experimental error does that introduce? Is your method effective at assessing the measurements you're taking? And those three categories together add up to the overall error in the data you're ultimately getting out of the system. Now, depending on the environment, depending on the use case, the relative importance of these will change. This study is primarily, as you'll see, focused on rigid body tracking. So, for example, even beyond this, if you're talking about biomechanics, while this is still somewhat informative, I think, for that use case, there are additional variables involved. The biomechanical modeling process is another variable on top of that. Are markers moving on the skin of your subject, which you wouldn't typically expect with rigid bodies, for example. So there are other things involved there as well, and differences to take into account in almost every use case, and not everything is exactly the same. A quick note about terminology. I've used the word accuracy a fair bit already. It's important to understand, just clarify exactly what that is, and just to lean on the International Standards Organization for definitions of this, and probably a diagram is to explain the context here. The difference between accuracy and precision, you can see the definitions for yourselves there, but essentially the main difference is accuracy is the error between an independent reference value that's obtained by a different measurement system. Precision is the level of agreement between individual observations or test results from a single measurement system. So you can have a high accuracy with a high precision, but you can't necessarily achieve a high accuracy with a low precision, but you could have a high precision and not a high accuracy, which is what the diagram to the bottom left shows. It is an important nuance, and particularly when you look at some of the methods, converting a measurement precision, which is generally the easiest to obtain, to an independent reference can be quite easy or very difficult, depending on the method you choose. Doesn't mean that the precision measurement is not useful, but if you're looking to really talk about relative to an independent measurement or a global measurement system, that distinction is quite important. And of course, when we talk about accuracy, there are even some differences in that. Are we talking about the difference to the average measurement, or are we talking about the range of all the measurements? There can be some nuance in that word, even so. So just to clarify what we mean in this context, so there's no confusion. And again, that's outlined in the FAQ as well, just to make that clear before we discuss some of the results, and in the white paper that's available as well to accompany this. So I'm not going to go through all the different methods we looked at and in detail and all the pros and cons. I think it's sufficient to say that there are a lot of different methods available, and they all have pros and cons. There's no right answer here. It's really important that you have something that is representative to your use case. So when we were looking at a method we would use to have this conversation, we were interested, of course, that it's easy to communicate, easy to understand, but also it's representative to a large part of our population of customers and users. We didn't want to choose something that really wasn't relevant to what people were using a system for, because that would change the outcome essentially. So you may have seen some of these before, and like I said, they all have strengths and weaknesses. The picture in the middle is my favorite. It's an early test we did, which is one of our most valuable pieces of equipment, a 1980s record player, which is just simply because it rotates and is very level. And we looked at the movement of markers moving in a circular fashion. It's a very good test if you're looking at that type of measurement, but it has some big disadvantages for the majority of our customers. It's fixed in one place in the volume. It's quite difficult to get a really good, accurate measurement of exactly what rotation you would expect. There is vibration even still in the turntable, particularly at the level we're talking about, for example. So it's difficult. That method in particular is quite difficult to convert precision to accuracy, for example. That's one of the weaknesses of it. It's still very, very relevant in certain cases, and that's something we looked at quite early on. Let's see. So let's move on. So I just wanted to talk about one experiment we did, which is not the data we'll be talking about in the results, but I think quite a nice example of these variables can affect the results you get. So this is welcome to Vicon HQ in this case. So this is in one of our test volumes. And this is a object that is oh, there we go. So this is an object that is at rest. Essentially, it's not moving the first part of the capture. And then the continuous capture, hello to Jack, hopefully you're watching, one of our support team, very ably rotating the object very gently backwards and forwards. This is a continuous capture. The system hasn't been changed. We did it as one capture, so there's absolutely no difference. The only difference is when we start moving the object, essentially. So we're as best as possible, we're controlling for that single variable. Of course, there'll still be a couple of variables in there, depending on what cameras are seeing the moving objects and things, but it's about as controlled as we could possibly manage. And the results of this are really quite interesting. So what we're comparing here is the distance between the two ends of the bar, so two rigid body objects at each end, and looking at that distance and how it changes frame by frame. And what you can see here is the dotted line is when we start moving the object, essentially. And on the left-hand side, it's quite a different picture to the right-hand side, shall I say. So it's much, much more consistent, and just comparing the difference in the errors before and after, essentially, I think is quite informative. And this is an example of controlling for one variable and making sure that we're trying to keep everything else consistent, just examine what this impact has. And in this case, it's quite significant. Now, I would argue that this is really quite significant for our method selection and why we did this in particular, because a motion capture system is typically, and I'm not going to say 100% of the time, but typically it's about measuring motion, of course. So what this is telling us is we need to choose a method that involves motion. Measuring an object that is still or at rest is really not representative at all of any of the types of data quality you would get out from a system in almost all situations. So that's a really important consideration. So having gone through those types of considerations, this is the method that we have ended up selecting. So it's a method that is published by the ASTM, the American Society of Tests and Measures, and the title is quite descriptive: evaluating the performance of optical tracking systems that measure 6 degrees of freedom. So very relevant title. I'll talk through some of the key points of the method and show you a little bit about how it's performed for the background. So the first thing is the object design. This is an object that's fixed, like we saw in the video before. It's fixed. It's a known length that can be measured. In our case, we use a coordinate measurement machine to get this exact measurement between the two groups of markers. And it gives us a very, very precise reference measurement. So essentially what we're examining here is that distance between those rigid bodies, which we know is physically not changing. And what we're doing is comparing that against the measurements we get out of the distance between those two objects from the motion capture system. Clearly, you can see here it's designed for a range of different types of technology, not just passive reflective markers. The object on the right is from more of an image-based system, which would deliver a similar output, but would look at a different type of object. The object is defined to be a particular size, a particular geometry to ensure consistency. And what you can see at the bottom is also it's defined to provide a standardized path. I mentioned before that every method has pros and cons, and in this method is no different. What you gain, in fact, it's quite a simple method to carry out. You lose because it's a manual method. So obviously anything that involves manual input is never going to be 100% consistent. I mean, in this case, it's someone carrying this bar through a volume. And we'll talk a little bit about how we can be confident that's still repeatable coming up. But of course, that introduces some variability. Do you go in exactly the same place in the volume? Are you managing to stay out of the cameras in exactly the same way so you're not occluding the actual test object, for example? It does introduce some variability, which, as we'll see, is not actually that significant, thankfully. But yes, so this is this is another video of us how the test is carried out. It's probably easier to see it being carried out. And like the diagram showed on the last slide, it involves walking up and down the volume in a number of different directions, in holding the objects in different orientations. And to show you what that looks like, those of you who are familiar with Tracker, our rigid body tracking software, this is what it looks like in the software. So you can see the object being tracked, moving up and down the volume in different directions. And this is one of the nice things about this method, of course, is that it collects data around the whole capture volume. It doesn't involve one fixed point in the volume, which obviously, again, for an object that's moving around the volume, that's very significant and captures that detail. What that does do is that actually makes this a tougher test. So in any given point in the capture volume, all of those variables we talked about before will add up to some sort of error distribution. Of course, we're adding another variable by moving around the volume, and that will make that error distribution change and essentially a cumulative error as you get different patches of variability based on other variables. So having said all of that, we actually did quite a bit of work, and this was quite a lengthy exercise to essentially validate the method before we started getting to assessing our own systems. And this is an example of the type of data set that's generated. So this is the measurement of the bar and the distribution across different trials. So in this case, this is 20 trials, and not just is it 20 trials to repeat the movement around the volume, but it's also across 4 different calibrations and 2 days. So what we're making sure is that not only are we assessing the consistency from trial to trial, which obviously is very important, it gives us a consistent result. We're also able to assess the consistency between different calibrations, and as much as is practical, potentially between different sets of environmental conditions as well. So does it change between days? Does it change between calibrations? And as you can see here, the red line is the actual reference value. Generally, it doesn't change very much. You can see the scale here. This is in half a millimeter, and graduations. And the mean, for example, the mean value across each of the trials was within 0.1 millimeter of the reference value, even for the outlier trials, which is probably this one here. So this is good news, because it means this method that we're using is consistent. I would say it's even better news when you consider it's a relatively simple method to perform, and especially compared to some of the other methods we looked at that might have involved specialist equipment, for example. So it's a good method, and should be representative for quite a large section of our customers, and like I said, at least informative for the rest about what our systems can achieve. So those of you that haven't seen the results, I'm sure are on tenterhooks by now to know what the results are. So here are the key figures. We looked at two different volumes, essentially, a very similar setup, but we looked at a setup with our V16, which is our highest resolution camera, and a Vantage V5, which is what somewhere in the middle of the range, essentially. We looked at, as we moved around the volume, how does it change, like I said, against that reference value. Both the two numbers we looked at earlier when we talked about accuracy and precision, the mean value relative to the reference, the difference is very, very small across that range of trials, 17 hundredths of a millimeter. Sorry, 1.7 hundredths of a millimeter. And that was consistent across the two trials. The standard deviation, so the range of those results, the average range, which again was very, very consistent from trial to trial, varied as you'd expect. So that the higher resolution camera had a lower variation as you moved around the volume, just under 0.2 of a millimeter standard deviation. The V5 was of course slightly higher, just over 0.3 of a millimeter. So, and I think just as interesting is, and I'll just zoom in on the results a little bit, this is one of the 20 trials in one of the sets. So particularly for those of you who use motion capture systems, probably even a little before, will know that typically you will have patches of coverage where it's not ideal due to constraints in camera numbers, camera layout. Various reasons could cause that, and what this pattern essentially shows is that you tend to have a very consistent area in the middle of the volume, and your outliers, not always, because we can introduce occlusions as we're moving through the volume, holding that bar. It's almost impossible to do that consistently 20 times, and you certainly get your steps in when you're doing this method as well. But outside of that, generally the outliers are at the edges of the volume, which is something that, like I said, someone who uses systems a lot will be quite familiar with when we have patches of coverage. So this method quite nicely summarizes that. It shows where the errors are coming from and what that distribution is, and hopefully that's informative and helps understand the pattern you can expect from this type of system, and some of the things that could cause that. So some conclusions and takeaways before we move on to some questions. Like I said at the beginning, Assessing a motion capture system is quite difficult, and it's even because it's easy to drift into the realm of it depends. It depends on several things, as many complex systems do. But it's even worse than that, because it superficially could seem a bit simpler than it is, and some of the variables and how significant they could be is maybe not as obvious as it might first appear. There is a very interesting study that the ASTM themselves did, where they actually looked at the movement of a wall with a laser measurement system in a building that cameras were mounted to. So nothing to do with the mounting of the camera themselves, just the structure it was mounted on and how that changed. And one of the findings was that an internal wall in the volume, same volume, due to the temperature changes outside the building, moved or fluctuated a lot less than an external wall. So where the wall was heating up and cooling down, the external wall in the building that was one side of the volume, it moved a lot more over a 24-hour period than the internal wall, because of those temperature changes it was experiencing on the other side of the wall, which is really interesting and is not something that would be immediately obvious. Obviously, some of the variables are more intuitive than that. The tests itself are from an external body, and we've really just validated that and added to that library of data. And it is a very capable method, and it's suitable, and it is relevant to what many of you who are users will be using the system for. Like I said, not all Vicon customers use our systems for a range of huge numbers of really interesting things. So it's impossible to do something that's very similar to all of those. But I think it's relevant to a large number of those use cases, which is really helpful, because as we've seen, how that method varies can be quite different. The changes in the method can be quite significant to the conclusion you come to. Of course, as we've just seen in the results, those numbers are to extremely fine margins. Without going back and going over the numbers again, I think as a relative newcomer to Vicon, I was actually quite surprised at how small those margins were. Probably quite impressive, I would say, of course. But also this study is a really good foundation for the future. Like I said right at the beginning, one of the things we really wanted to do was provide a baseline of where we are for future developments, future camera variants as we move forward. And of course, different conditions that you would have seen that the study was indoors. So for example, like what happens when we take that outdoors, other edge cases in that nature that we can build on in the future. Obviously, it's a significant investment and work to do this well, but as we build up that library of data, I think it'll be really informative going forward. So, hopefully that was helpful for you. Roughly a half-hour summary of the project we did, and added some context to what we did and some of the results and some of the conclusions and takeaways from that. And with that, Alicia, maybe we can open it up to some questions.
Yes, looks like we have quite a few stacked up if you want to take a look at that.
All right. Maybe we could just, while I go through the poll, maybe I thought that would be quite interesting, just while I have a quick look at what questions we've got. Would that be okay?
Yeah, I think everyone should be able to see the results. It says I'm sharing them, but it looks like 29 people are gait analysis use case. So I'm not sure if everyone can see these, but
let's have a look. Yeah, so it looks like we've got, it's not really surprising, we've got a range of people from different backgrounds, so quite a few from life sciences, gait analysis. So for those of you who aren't tracking rigid bodies, hopefully this is still, you can see how this would be helpful and informative for you. And as I touched on in the presentation, there are a couple of, there are some more variables, of course, with biomechanics. I'm an engineer myself, so I can say this, but obviously biomechanical modeling has a few extra pieces of complexity involved. So that's layered on top compared to what we're doing with rigid body tracking. But I think even so, it's a good foundation for having a discussion about what our systems can achieve and understanding some of the factors that can have an impact on the tracking quality. So yeah, hopefully that was interesting for everyone, regardless of your background and what you're interested in. So maybe it'll take some minutes to go through some questions. So Alicia, I don't know if I'm supposed to click on the button as we go through, but I'll just read them out. So first one is, I think maybe this was answered later in the presentation, but if the rigid body recording says it's stationary RMS, what will be the error RMS if it's moving at walking speed? So again, that's actually the main, like I said during the presentation, the main thrust of this study is to look at a moving object, and as you would have seen maybe later in the presentation, the actual data we published is based on an object moving, funnily enough, at walking speed, so someone carrying it through a volume. So again, that discussion about relevancy and to the use cases, that's a good example of that. I think this will be quite informative for that. Let's see. Yeah, good question. So how do we determine the reference length of the object? So I mentioned in the discussion we used a coordinate measurement machine, which is accurate to millionths, multiple millionths of a millimeter. It's an extra significant figure than what we used here, but it's obviously that type of system is only used for fixed measurements of static objects. So it's a good reference. What it's not able to accommodate is an object that's moving around the volume. So it's we use that fixed length as that reference, as I talked about, and then as we move around the volume, we can see how it changes. So yeah, we have a high confidence over that reference to an extra significant figure. Can you tell us the maximum and minimum observed length? Yes. Well, again, it varies by data set, and it doesn't have it on this table, but yes. So essentially, the outliers here. So this is a capture of the frame rates of the two cameras were slightly different, but we're looking at around about 50,000 frames of data here. And the outliers in general are, in this case, a millimeter and a half outside, plus or minus. So again, they're very, very extreme outliers. And like we talked about during the discussion, you would get those, they occur in areas of very relatively weak coverage at the edges of the volume. And the difference between the middle of the volume and the edge of the volume is where you see those variances, essentially, except where we're introducing occlusions, as I was talking about. Could this type of test be performed with a calibration wand? I don't think so, which is why we didn't use one. First of all, the standard, the calibration wand doesn't conform to that standard. So that's one reason. But the calibration wand is not two rigid bodies. So I think it would be difficult and unrepresentative to use that as a test object. I would recommend an object is constructed that conforms to that standard or very similar construction to produce, again, like we've talked about through the presentation, a result that is representative of what you'll actually be testing, unless a calibration wand is very similar to what you're tracking, in which case it might be appropriate, but I think that's unlikely. you would want something that's representative to what you're actually doing, essentially. Let's see. Yeah, so this is an interesting question. Does the accuracy depend on the size of the markers? So I would say not significantly. We haven't actually got any data between different sizes of markers. It's more of a threshold question. It's quite a technical. I'm trying to think of the right way to. Essentially, it's not a linear relationship. So you will see some changes, but obviously the big difference is when the markers are no longer visible, and then that has a dramatic impact. You stop tracking. So if for whatever reason that may be, so I think that's where it does have an impact, of course. But in general, changing the size of the markers is significant up to a point, and then is less so provided the markers are very visible. It, of course, is a variable and has an impact. I haven't got any data to talk about those differences, but it will be a variable. Yes, so someone's actually said, maybe in their own experience, opening a door was enough to tilt a camera that was mounted, and that was enough to cause some error. Absolutely. I mean, we talked about the temperature changes example, which is quite subtle, but would have an impact in definitely more severe vibrations. Maybe if someone slammed the door, it'd be worse. So it's absolutely, and again, that is and it depends. If the mounting position is well damped and doesn't suffer from so much vibration, it's possible that impact could be quite small. If it's not, and someone slams a door particularly severely, for example, or something, it will have more of an impact. And of course, is the camera significant at the point you're measuring, or is the object over on the other side of the volume, for example? All of those come into play. But yes, something like that can definitely have an impact, depending on the situation. Is this paper available online, which describes the study? So yes, I'll just make a quick plug. I'll take the opportunity to do so. So a lot of this information, and there is an FAQ on vicon.com where you can read a little bit more about this. We've covered a lot of the material here. But there is also a white paper that goes through, again, covers a lot of this material, but you can read about. So I just say, if that interests you and you'd like to read more about this, please contact your relevant Vicon representative, who would be happy to assist you with that. That's available. Let's see. So question, what are the methods to increase the accuracy of a Vicon system? It's a very big question, because what we've spoken about already is there's a lot of variables involved, and probably would justify a full other session in itself. Obviously, my first comment would be, if you're curious about that, contact our friendly support team, who are excellent, real fonts of knowledge, and have huge amounts of experience in many of the things we've been talking about. This is not, although the study is new, this type of knowledge is not new to Vicon. We've been around for a long time, and there's a lot of knowledge about different use cases and what will work well for you. And I would encourage you, our support team is absolutely fantastic. But of course, there are some best practices. Calibrating regularly is one common recommendation, because that removes a lot of the variables that will occur over time that will incur drift, for example. But making sure cameras are well focused, well maintained. Your environment is consistent. You don't have too much temperature fluctuations, which can can affect not just the cameras, but the mounting, thermal expansion. There's a very interesting example of that outdoors where the sunshine would shine onto a camera mount, which was a long pole. One side would expand, and that would warp the mount slightly, and that would affect the data quality. So there's a lot of different factors, and some, like I've said, that wouldn't apply indoors, of course. So it depends a lot on your environment and what variables are most significant. But yes, general good practice and making sure the system is well set up, well maintained, calibrated often, I think is the best general advice I can give. So a question about the observed error is due to variability between calibrations and how much is due to the algorithms themselves. I think, I'll find the right slide. I think this is, for me, a very interesting slide, a very interesting data set, because it shows the difference between calibrations between days. Now, because it isn't really practical to do this over a long period of time, because that would mean we aren't controlling for other variables. But this is over 2 separate days. For those of you who may not be familiar with Vicon HQ, we have some temperature fluctuations, of course, like any building would, and similar types of things from day to day. So it's quite a valuable test. And I think the conclusion is it doesn't change that much. It relies on someone, performing a calibration according to best practices, performing it regularly, making sure that the calibration is done in a very visible manner, those types of things. But I think in general, following good practice, the answer is not too much. Of course, that will vary according to the environment and where you are. But I think other variables are surprisingly large. I think camera mounting is probably the most common thing that I see. Someone hasn't done, or it's loosened over time, and that camera has not slackened off enough to move suddenly and very noticeably, but it's moving very, very slowly over time. So just making sure your cameras are mounted securely, I think, is a good step from time to time, and it's good best practice. Yeah, so let's see. Do you have any results or studies on multi-quad rotors with loads? So no, we don't. But I'd say this type of method we were talking about, representative uses, rigid body tracking in general, I think is very applicable. It's essentially what we're testing here. So I think that type of use case is very relevant, and would find a lot of similarities to this test here. So I think I'm encouraged to look through this in a bit more detail. And like I said, some use cases will be slightly different, but I think we'll still find this informative. So question about the method itself. Variability about the way the object is held by the person holding it, walking through the volume. Were you consistent in the way you held it, overhead, out in front of the body while you were walking, object held towards cameras? So the short answer to that is, as much as possible, yes. It over multiple days, like I mentioned, we got plenty of steps in on those days. It's quite hard keeping your arm above that head if anyone's done any plastering on a ceiling perhaps or something. It's quite difficult to hold that position for a long time completely consistently. So it was a good workout, but as much as possible we did that. It is very, very difficult even within trials to keep out of the way of all the cameras, and move that object completely consistently and smoothly. And as I mentioned, that does inevitably introduce some additional variability, which has nothing to do with the observation of the system themselves. It's just some of the experimental error that's inherent in the test. However, as you can see from this, it's relatively small. And when you look at the analysis, it's possible to pick out where outliers may have been produced by that. In general, that didn't happen, but it's impossible to completely eliminate. So yeah, so another question about my screen. Lost the question. Was this using standard default parameters? Yes, actually. So this was vanilla tracker essentially. There was no real optimization, really deemed necessary in this case, and wasn't really changed. Of course, there are a lot of features in Tracker that are designed to help with different use cases, different scenarios, which we would use. But in this case, there wasn't deemed necessary, and this is standard Tracker setup essentially. Let's see. For one, calibration is more samples, more accuracy. I'd love to have one of my technical colleagues, Paul, who could talk about this in a great amount of detail. But yeah, in general, yes, up to a point. There's obviously diminishing returns as you add more and more frames. Hopefully, Paul, if you're listening, I'm representing this well, but just as important to the number of frames is the quality of those frames. So do you get good coverage around the camera lens? Do you provide it with enough disparate data to achieve a really good calibration? So the technique of waving the wand, in most cases, is perfectly adequate. There are some techniques where you don't collect that good array of data around the camera lens, and that may adversely affect the calibration. So a combination of number of frames, but also the quality of that data you're providing to the calibration algorithm to give a good calibration is always beneficial. Let's see. Kathy Holt found that a diamond-shaped reflective tape stuck to the skin are better than round. Any advice on shapes? It's not really my area of expertise, and I could only guess at why that might be. I guess because it prevents confusion with an actual marker. If I'm understanding that correctly, but I don't know. There's probably a question for our life sciences team. I'm sure Plug again, our support team would have some great input on that, I'm sure, and some good advice. Let's see. Your test object on the edge is a 2D position orientation, markers aligned in one plane. What is the reason for placing the markers this way and not in a 3D position? That's not, maybe I can go back to the picture of the object to answer that. That's not strictly true. It's a little bit difficult to see from this picture, but there is actually a third marker which is sticking out from the ends of each bar, which makes a 3D shape. Yeah, good question. I mean, yes, the 3D object is obviously more relevant again. It's purely because of the metrology equipment that's been used here to build a frame is basically at right angles. So a large proportion of those markers are planar, but not entirely. So hopefully that's clear from the picture. Yeah, so another question that's just come in. Can we talk about how we calibrated, how many frames? I would actually have to check my notes. I can't remember the number of frames. I think it was a 3,000 frame calibration, which is the default for Tracker. I believe that's the case. And yeah, the calibration process was what we would consider a standard process, a standard one wave, an origin set. The one thing I would add is making sure the object using to scale the volume is very visible. If you're interested in that, reference to a real world measurement is good as well. And there are some good best practices around that as well, which came out of the study. Another plug, more recent updates of Tracker have included some additional functionality to help make that reference so you can get the best possible results. So I'd encourage you to look into that, and there's some notes in the most recent updates of Tracker. I'm afraid the questions have been coming quite thick and fast. I think a lot of them are hopefully repeats of what I've answered. I apologize if I've missed any. How are we doing for time? Just coming up on time. I'll see if I can pick one more to answer. Let's try and find something that we haven't really answered so far. Let's see. I've probably answered that one already. The one question is the quality error graph in Tracker software a good indicator of how precise the measurements are? I mean, yes, to some extent. There's obviously some information that we don't have when an object's created about the exact size of the object. That's why we have to perform an external reference, and a lot of our work is measuring that. But I would say it's closely related to the precision. For example, we're not able, without some of the scaling that I talked about earlier, to provide a real world measurement. It doesn't necessarily tie directly to that unless that step's performed, but as we've seen, it's very consistent anyway. But yes, it would tie closely to the precision, essentially, the results we've seen. Okay, Alicia, I think we're kind of at time. Anything else to say before we close?
No, I don't think so. If your question did not get answered, or if you have further questions, then definitely just email us at support@Vicon, and we will be happy to expand on any of this. The recording of this whole presentation will be in your inbox tomorrow, and you can message us support@Vicon, marketing@Vicon with any other questions about that, if you'd like to get the white paper, and definitely check out the FAQ section. I will post the beginning of it here in the chat if you'd like to go and check that out now. But I think that'll do it. So this is also on YouTube. The stream will be up right away if you'd like to share it, and just let us know if you have any other questions or comments.
Great. Thank you very much for joining, and hope to see you next week. Dr. Tom Shannon is doing a great talk I'm really interested in, really looking forward to, and hopefully we'll see you there too.